yeah. So way back when we started talking about derivatives, we said the derivative had 3 important components to it, or the derivative was defined as 3 things. What are they?
Rate of change.
Rate of change, excellent. Velocity, which velocity?
Initial.
Instantaneous, correct. And? Slope of the tangent line to the curve, very good. There is also a physical application of the antiderivative or the integral, and hopefully you've noticed by now that I use those 2 terms interchangeably. The integral of a curve is the same thing as the area under the curve. And meaning if I take a picture of whatever function we're talking about, the integral will be the area under the curve. And initially we're not going to be able to find that number, but we're going to start with some approximations. Okay, so let's go through this. We'll talk about the concept of area. We're going to look at 4 different ways to approximate the area under the curve by drawing rectangles. It's basically a geometry lesson today. Then we're going to talk a little bit about some limits, not too much, just enough to put you on edge. And then you should continue to practice drawing the squiggly thing. How many people have it under control?
Not even close.
Oh, nice. Not even close. What's yours look like, an S?
Mine's kind of like, sometimes it's an S, sometimes it's an I, sometimes it's an
So
L.
no consistency whatsoever.
It's just like, you just...
What, like you're having a seizure?
Sometimes it's like a musical note, just
They're
like...
horrible.
No.
You just kind of just fire them off.
It's kind of just like how you draw. It doesn't really matter, does it?
Okay, so here we go. As I already mentioned, the integral of a function will be defined as the area under the curve. Now obviously we're going to have to take a range here. We can't take the area under the entire curve because that would be infinite. So we're going to have a starting point and a stopping point, commonly referred to as A and B. A is the starting point, B is the ending point. And we're going to take that area and we're going to split it into a bunch of rectangles. So here's my curve. This is f of x, the red thing. So here's f of x. And I chose to take this area from 0 to 10 and split it into 1, 2, 3, 4, 5 purple rectangles. There are 5 rectangles going from 0 to 10. How wide is each rectangle? 2. How do you know that?
10 divided by 5 is 2.
Say what?
10 divided by 5 is 2.
Excellent. Now suppose I go from 100 to 200 and I have 20 rectangles. How wide is each rectangle? Why?
Because 200 minus 100 is 100. 100 divided by 20 is 5.
Perfect. Now suppose I go from A to B and I have n rectangles. How wide is each rectangle?
B minus A over n.
So as you can see by these little dots in the corner, I didn't want to be in that mode. Well done, Peyton. So delta x is the width of the rectangle, and the width of that rectangle is found by doing b minus a divided by n. It's not always going to start at 0. Sometimes, well, not a lot of times, but it could be over on the negative side. But for the most part, we're going to be in the first quadrant. B minus a divided by n. Okay, going back to that other mode then. We have some wasted space here. That little guy, that little guy, that little guy, and those little guys. So this is why it's an approximation. The question is, how do I get rid of that blue area, that wasted space? What can I do to make my answer more exact?
Area of a triangle.
I'm sorry?
Area of a triangle.
What about it?
Find each triangle. I don't know.
Not a bad idea, and we do that later. Instead of using rectangles, we'll change the shape of the thing underneath, and that'll give us a more accurate answer. But staying with rectangles, how can we shrink the wasted space?
More ends.
I'm sorry, what?
More ends.
More ends. Okay, in other words, increase the number of rectangles.
Yeah.
Okay, as the number of rectangles goes up, delta x is going to get smaller. So we're going to say the same thing 2 different ways. Either we want delta x to get really small, or we want n to be very big. Does that make sense?
Yep.
Okay, if my rectangles get skinnier, I'm going to have less wasted space. All right. Initially, we're just going to start, like I said, doing a geometry problem. We're going to find the area of each one of these rectangles, add them up, and when we're done, we get an approximation of the area of the rectangle. Okay, so let's start with this middle rectangle. You answered this question already, but I'll ask it again. How wide is that rectangle? 2. Good. How tall is that rectangle?
Around 6.
Around 6 isn't going to cut it.
5.5. It's definitely more than 5. Come on.
It's more than.
Give me that.
F of 2.
5.5. You say
So
half
a lot of ambiguity
F of
in
2.
there.
I'm with blood.
Hmm?
I'm with blood on this one.
What?
F of 2.
F of 2, I like that also. But it's not F of 2.
Four.
F of 4, correct.
Oh.
That point is crucial.
I just saw a 2 out there. I can't read those numbers.
Oh my gosh.
Unless we do the smaller, right?
I understand. That distance is the height of that rectangle, and the height of that rectangle is F of 4. How tall is this rectangle?
F of 8.
F of 8. How tall is this rectangle?
F of 6.
F
F of 2. F of 0.
Good.
Right.
Assuming we knew what F of X is, how do we find F of 4? Plug it in. Okay, you know I don't like pronouns. What's the-
Plug 4 into the function.
Plug 4 into the function. Well done. Okay?
It's a little.
So that's the whole idea of what we're going to do. Now, what we go from that point on is we change the different types of rectangles we can use. So let's go to learn how to use that. Oh, yeah, there it is. So these are called left-hand rectangles. They're called left-hand rectangles because the left-hand side of the rectangle is what hits the curve. So when I drew this picture, I drew in my divisions here, drew up these vertical lines or segments, and then went up the left-hand side of the rectangle. When it hit the curve, I went across. Go up the left-hand side of the rectangle, hit the curve, go across, etc., until I get my 5 rectangles. You'll notice in this particular picture, the left-hand rectangles are below the graph. That's not always going to be the case, just in this example. This, by the way, is called an underestimate. It's called an underestimate because the area of the rectangles is going to be less than the actual area because I have wasted space. All right, you with me so far? So there's the formula for finding the area of that thing. I wouldn't memorize formulas. It's just geometry. Find the area of each of those rectangles, add them all up. We're good? Yeah, good. Right-hand rectangles. Same idea, same picture, drew my vertical lines. This time, however, when I go up the right-hand side of the rectangle, when I hit the graph, I come across the other direction. Come up the right-hand side, hit the graph, come across, etc., etc. Any idea what that's called? Overestimate, correct. The area of the rectangles will be bigger than the actual area under the curve. And notice my F of things changed. In the other one, we went 0, 2, 4, 6, 8. This one goes 2, 4, 6, 8, 10. Because, again, we're looking at where it hits the curve. We good so far? That's the first two. Left-hand rectangles and right-hand rectangles. So you'll always go up the left-hand or the right-hand side, depending on which one you're using. So let's look at this example. I've got a little curve there, 1/2 x squared plus 2, and I want to use 3 rectangles in the interval from 1 to 4. Question number 1, what's delta x? Whoops. Yeah.
1
Why?
plus 4 minus 1 over 3.
Starting at 1, ending at 4, breaking it into 3 rectangles. We'll start with left-hand rectangles. So what I do is I go to 1, I draw in all my vertical lines first. So there's 1, 2, 3, and 4. Left-hand rectangles. So you go up the left-hand side, hit the function, come across. Go up the left-hand side, hit the function, come across. Go up the left-hand side, hit the function, come across. So I want to find the area of these things. And again, don't turn this into a big complicated problem. Just turn it into a geometry problem. Each of these are 1 unit wide. How tall is the first rectangle? F of 1. Correct.
Wait, oh, because it's touching the curve on the left side.
You got it. Okay. How tall is the second rectangle? F of 2. And how tall is the third rectangle? f of 3. And delta x is equal to 1, so I'm going to put a 1 out in front. So instead of doing base times height plus base times height plus base times height, I just factored out the width, or the base, and then do that. What's f of 1?
2.5. 3 halves.
3 halves or 2.5?
Oh wait, 2.5.
2.5, which in fraction form is?
Not 3 halves.
Is not 3 halves, correct? Good. 5 halves, good. What's f of 2? 4. And what's f of 3?
6.
By the way, in case you guys aren't following, where are these numbers coming from?
Plugging
Plugging into the function, correct. So what's f of 3?
13.
Which gives me 5 halves plus 8 halves, 20, 13. And again, if you look at the picture, that's an underestimate because I have wasted space. Any problems before I move on to right hand? We're good? Aces. Okay, right hand rectangles. I'm going to use the same vertical lines. But this time I go up the right-hand side. So I go up the right-hand side, I hit the function, come across. Go up the right-hand side, hit the function, come across. Go up the right-hand side, hit the function, come across. So the area using right-hand rectangles. Delta x did not change. How tall is the first rectangle?
4.
F of 2. Second rectangle? F of 3. And the third rectangle? F of 4. For those of you that are good at pattern recognition, you'd see how that works. F of 2 we did already, that's 4. So 1 is 4. F of 3 we did already, that was 13 halves. And so we need F of 4, which is 16a 10. Which gives me a value of 41 halves. Yes? You sure? You were the 3 halves guy before, so I don't know if I can trust you. And again, that would be an overestimate because notice we have area of the rectangles that are outside, or I should say above the curve that we started with. The easiest thing, well, I shouldn't say this, the best thing you can do to help yourselves with these problems is draw a nice graph. Because then you can visualize exactly where your rectangles are, how tall each of the rectangles are based on which side you come from. You come from the left or come from the right. Add all those up, you're good to go. Any problems? Okay. Again, don't think that left-hand rectangles are always underestimates and right-hand rectangles are always overestimates. It can change depending on the shape of the curve. We're good? Moving on. Oh, this is all the work to show you. Oh, look there. There. Good. 13. Is that what we had?
Yeah.
Good. And then what do we have for the second one? 41 halves.
Yep.
20.5. Good. So I did my math correctly. Yay! Upper and lower sums. The two other types of rectangles we're going to talk about are summarized in this picture. So let's start with the middle picture. The middle picture is the exact area under the curve. So there's no gaps there. There's no wasted space. It hits in every single point. Delta x in this case would be 0. And n would be
0.
no, infinity, correct. So we'd have an infinite number of rectangles there. Inscribed rectangles are rectangles that are always, regardless of whether it's left hand or right hand, always below the curve. So notice that this rectangle is a left-hand rectangle. However, if I jump over here, this one is a right-hand rectangle. So left and right hand don't matter as long as you keep it below the curve. So again, draw your vertical lines upward, hit the curve, and then decide do you go left or right based on what it takes to keep it below the curve. So inscribed is below. On the far side, circumscribed, are rectangles that are always above the curve. So notice each of these rectangles has a little smidgen, and that's a word, above the curve. With these two, we can make some general statements. Inscribed rectangles are always underestimates. Circumscribed rectangles are always overestimates. With left-hand and right-hand, you can't do that, but with these two, you can.
Is that only rectangles?
Yeah. Oh, wrong button. There we go. So again, another smaller version of what's going on. Inscribed below, circumscribed above. Possible example that we don't need to necessarily work through. Going from 0 to 1 and using certain number of rectangles will give us that function. And then we're done. Day 58 for homework.